Okay, today we're going to go over the final solid geometry part 3 homework. Let's get to it. Question number 1. What is the volume of a hemisphere that has a diameter of 12.6 to the nearest tenth of a cubic centimeter? Okay, so we know that the volume of a sphere, right, the volume of a whole sphere, I'll put it down here, is 4/3 pi r to the third power. That is on your reference sheet. However, a hemisphere technically means half a sphere. So it's really half of 4/3 pi r to the third power. And if we simplify that, 1/2 times 4/3, you get 2/3 pi r to the third power. So that's where we begin with our formula. The volume of a hemisphere is 2/3 pi r to the third power. And the only thing we need to know is the radius. Well, I'm just going to use the RD of our card. Well, it's because they're giving us 12.6 as the diameter, which means the radius is going to be half of that, which is 6.3. So I'm going to come over here, substitute 6.3 to the third power, and I can see that they're not giving the answers in terms of pi. So I am just going to open up the calculator, go 2 divided by 3, which is how I do my 2/3, second power, which is my pi. I am going to put that in parentheses just to make sure that it multiplies. And that's going to be to the third power. And I could see that it's to the nearest tenth. It should be 523.7. 523.7 cubic centimeters. Okay, now we're getting a little bit more complicated. A bakery, number 2, a bakery sells hollow chocolate spheres. The larger diameter of each sphere is 4 centimeters. The thickness of the chocolate of each sphere is 0.5 or half a centimeter. Okay, there's 2 parts to this question. Part A, determine and state to the nearest tenth of a cubic centimeter the amount of chocolate in each sphere. And then B, the bakery packages 8 of them into a box if the density of the chocolate is 1.308 grams per cubic centimeter. Determine and state to the nearest gram the total mass of the chocolate box. Okay, that has to do with one of those mass volume density problems that we learned last class. Well, let's start with part A, just finding this somewhat more complicated volume of the chocolate. Well, I drew this little diagram just so you can get an idea here. So really what they're saying is that we have a diameter of 4, the larger, right? So that means if we, put a line right across here, right? That's going to be 4. So really what this is when you look at the sphere two-dimensionally, it really becomes instead of the area, find the volume of the shaded region, right? We really just want to know how much chocolate's in this outer part right here. And they did tell us that it's 0.5 in thickness. Well, if that's 0.5 there, then it's also 0.5 over here, which makes this other diameter of the space that we don't want to be 4 minus half here minus half, which is 3. which really means we're dealing with two spheres. And since we only want the shaded region part, it's going to be the volume of the larger minus the volume of the smaller, like when we did the area of the shaded region, except now with volume. Well, they're both going to be spheres, right? So we're really going to have, for part A, the volume of a sphere, which is, so the volume of the chocolate is going to be the sphere 1, which is 4/3 pi r to the third power, minus the smaller sphere, which is also 4/3 pi r to the third power. So we really need to decide is what's the radius of the larger and what's the radius of the smaller, right? We have got two r's, like r1 and r2. Well, our r1 of the larger is going to be half of 4, which is 2. And the radius for the smaller is going to be half of 3, which is 1.5. So I'm just going to say our overall volume for one chocolate is going to be 4/3 pi 2 to the third power minus 4/3 pi 1.5 to the third power. So I'm going to come over here to my calculator and just put it in there because it's really just wants it's the nearest cubic inch. So why not get it all in there? So 4 divided by 3 pi 2 to the third power. I know what that is, but I'm still going to put it in there. 2 to the third power. Now here I got to get down from my power. You hit the right button. And I'm going to subtract from that 4/3 pi 1.5 to the third power. Enter, and we get right there 19.3731, right? And it said to the nearest, what? Determine the states of the nearest tenth, the amount for each. Okay, just for one. So it's going to be 19.4 cubic centimeters per chocolate sphere. Now here it says the bakery package is 8 of them in a box. So if the density is 1.308, determine states the nearest the total mass of the box of chocolates. Okay, well, so obviously here the other day we learned that mass is equal to density, which we're usually going to be given, times our volume. So our volume is something that we're going to be finding in most of these problems. Well, we have the volume of 1. So first we have to do the volume of 8. So our final answer here is really going to be 19.4, which is the volume of 1, times 8, which will be the volume to the nearest tenth of 8. And then that'll be our total volume. To get our mass in grams, all we got to do is multiply that by our density. And that should give us to the nearest whole number. So I'm going to got my calculator out. I'm actually going to be a little bit more accurate. I'm going to use this number right here, right there. I'm going to multiply that by 8. And then multiply that by 1.308. And that gives us our final answer, 203 grams of chocolate. Yum, 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 yum. Number 3. The greenhouse pictured below can be modeled as a rectangular prism with a half cylinder on top. The rectangular prism is 20 feet wide, 12 feet high, 45 feet long. The half cylinder has a diameter of 20 feet. To the nearest cubic foot, what is the volume of the greenhouse? Right, this is classic compound area. We did one of these, a couple of these in class last week. So compound area just means to find the volume, or compound volume, the volume of the figures when you break them down into recognizable figures that have formulas that are given to us. Well, here we have a rectangular prism plus a half cylinder. All right, so our total volume of this greenhouse will be the rectangular prism, which is length times width times height, plus a half cylinder. Well, a half cylinder, if a whole cylinder is pi r squared h, then a half cylinder is just half pi r squared h. And that's really it. That's pretty straightforward. So here, let's take a look at the length, the length, the width, and the height of the rectangular prism are all given to us. The length is 45, the width is 20, and the height is 12. So that we can just get that substituted in here. 45 times 20 times 12. And then we get to here, and there's only one variable that we need there, or two, I should say. We need the radius and the height of the half cylinder. Well, they gave us the diameter of 20, which means the radius is going to be half of that, which is 10. And the height is really if you stood up a cylinder on its base, which is a circle, how far back it goes to the other half circle in this case, which is 45. So I'll put a little 10 in here and a 45 in there. And now, since we're rounding this off to the nearest cubic foot, again, let's go to the calculator. Let's clear this out. It's getting a little confusing there. So 45, I'm not going to put the parentheses for those, times 20 times 12. That's the volume of the rectangular prism, plus 1/2, which is 0.5, pi. Now I'll use the parentheses. 10 squared times 45. Now, if I put that in right, that should give us the right answer. And it looks pretty good. It says to the nearest cubic foot, so 17,869. 17,869. And that's going to be cubic feet. All right, let's move on. Let's keep on going. Okay, another classic Regents compound volume question. A storage tank is in the shape of a cylinder with a hemisphere on top. The highest point of the side of the storage tank is 13 meters above the floor of the storage tank. The diameter inside the cylinder is 8 meters. Determine a state to the nearest cubic meter, the total volume inside the tank. Okay, I remember this problem, and I remember where it was tricky. But first, let's just take a look at what we're finding the volume of. This is a cylinder and a hemisphere. Well, let's do the cylinder. Well, the cylinder is going to be pi r squared h plus the volume of the hemisphere, which we should know by now is not 4/3, but half of that, which is 2/3 pi r to the third power. All right, so in this problem, we really just need the radius and the height of the cylinder, because that radius is going to be shared between both of them. Well, the radius is the easy part. The radius is going to be half of 8, which is 4. The height is where I remember a lot of people making a mistake, because this is the height of the cylinder. So the cylinder height stops right here. But this 13 is really this whole thing. So it's really, this is the part we want to know from here to here, minus this part right here, because the 13 goes to the top of the hemisphere. So the trick of this was knowing that since the radius up here is 4, as it is down here, that radius is, part of the formula, radius to the third power. That radius is three-dimensional in a sphere, which means it goes in every direction, including up, which means this will also be 4, which means this part right here is also 4, which means the height of the cylinder is going to be the 13 minus 4, which is 9. That was the tricky part there. So now we could substitute everything in. Pi r squared h plus 2/3 pi r to the third power. And again, we're going to go to the calculator here and just put that in. Why not? So here we go. Second pi 4 squared, being very technical here by getting this all in the parentheses. Okay, so that's pi r squared h, there's our cylinder, plus 2/3 our hemisphere, pi as well. The radius to the third power. And there we have it. And it said to the nearest cubic meter, so 586 cubic meters. Oof. Okay, so look, I did put a bunch of these really just so you could get an idea of where we would have gone should we have had more time together. However, this was a 6-point question on a Regents exam, so it would have been our reality. All right, so they break it down here into 3 parts. So let's take this one at a time. Question 5, a rectangular in-ground pool is modeled by the prism below. The inside of the pool is 16 feet wide and 35 feet long. The pool has a shallow end and a deep end, which is a sloped floor connecting the two ends. Without water, the shallow end is 9 feet long and 4.5 feet deep. And the deep end of the pool is 12.5 feet long. Right? All of those numbers are put in there for us that we could see right there, including the beginning of this part A. If the sloped floor has an angle of depression of 16.5 degrees, which they show us there, what is the depth of the pool at the deep end to the nearest tenth of a foot? Okay, so they're really asking, how deep is the pool here? This is the question. How deep is that right here, that dimension? Well, one of the tricks to these really complicated compound questions is breaking it down with your own imaginary lines, however you feel that you want to put them, to create shapes that we're more familiar with. So one thing I'm going to do right here is I'm going to take this little line right here, dotted line. I'm going to move it right across and create a rectangular prism there. And just to keep the perspective, it also goes, right around there. And then of course it goes right across there. Okay, so what I've done is I've helped us find a part of that depth of the deep end, right? By putting that line across there and creating a rectangular prism, I know if this is 4.5 feet, that this part right here that I drew also has to be 4.5 feet, right? However, it's this part that we need to find, right? This is the question mark. This right here is our x in this problem. And then I can just add it to the 4.5. Now I create another little rectangle here through that, which means if this is x as well. And what we're seeing form over here is something that's very common in these problems. Well, they wouldn't have given me that angle and have created what is clearly a right triangle if they did not want me to use right triangle trigonometry. So that's something that we have to come to recognize. So up here, just to remind myself, I'm going to put a little SOHCAHTOA because that is going to be necessary here in order to find this missing measurement. However, you might remember that SOHCAHTOA, right triangle trigonometry, we need two sides involved, right? One that we're looking for in this case. We need one of these other sides. We have the angle that they gave us. Well, this side right here is going to be acquired by this big line right up here, which as we can see over here is 35 feet, right? Well, if we take that 35 feet up there, we'll do it over here, of that long side, and I subtract away this 9 feet, and then also subtract away 12.5 feet, take away the 9, take away the 12.5, you end up with, what, that's 21.5, I think you end up with about, let's make sure, let's not leave anything to Mr. Frank making a silly mistake. So 35 minus 9 minus 12.5. I think it's about 16, 13. So we get 13.5 feet right there. So now we can see this little right triangle here. And I'm going to go through my SOHCAHTOA. Now, if I do my SOHCAHTOA, you know, this X right here, that's going to be my, right, remember, bow and arrow? It's going to be my O. And this is the hypotenuse down here. I don't need that. So this right here is going to be my A. So it's an O and an A, which means it's going to be a TOA problem. So let's set that up over here. So we're going to have the tan of 16.5 degrees is equal my O over my A, which is going to be my X over 13.5. I'm going to cross multiply that, and I'm going to get my X is equal to 13.5 tan 16.5. And it's said to the nearest, what, nearest tenth of a foot. So I'm going to take out my calculator. Oh, remember, calculators have to get switched into degrees when we're doing trig. All right, let's get that done. And I'm going to have 13.5 tan 16.5. And I'm going to hit enter. Oh, and it's going to give me 3.99. That's going to give me 4.0. Look at that. 4.0 to the nearest tenth. 4.0 feet. So that means that this right here is 4 feet. And this part over here is 4.5 feet. Well, 4 plus 4.5 is going to be 8.5 feet. So how deep is the deep end? 8.5 feet. There you go, a little trig, right? And now we also know it could replace this number up here if we would need it with 8.5. We'll see. We might need that in a minute. All right, there you have it. So let's see if we can figure out now, part B, find the volume of the whole entire pool. Oy, 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 oy. All right. Well, let's see what we have here, okay? To find the volume of the pool, I'm seeing the way that I drew this line across, I'm seeing 3 figures now that we're going to have to find the volume of and then add together. This large rectangular prism on the top, this smaller rectangular prism down here in the deep end here, and then a triangular prism. A triangular prism, right? Okay. All right, so we're really going to have, if I had to write it all out over here, I'm going to disconnect this here. Okay, work over here. So our volume of the whole pool is really going to be length times width times height of our first rectangular prism. Then I'm going to add another length, width, and height of this one over here. So I'll say this is going to be like our first one. This right here is going to be our second one. And then the third one is going to be this triangular prism. Well, a triangular prism is really big B times H. But the big B, the base of a triangular prism is the area of a triangle, which is 1/2 small b height. So this is really my big B. It's really going to be 1/2 my base times height, which is my big B, times the height, right? So you have a height 1 and a height 2 in that case. A little tricky. All right. So let us begin. Let's see if we can get all these numbers. Well, I think we have most of them, so we can just get them all in here. So we're going to have the volume is equal to, let's do our first rectangular prism is going to be 4.5 by 16 by 35, right? 35 by 16 by 4.5. And then we're going to add, I'm running out of space here. We're going to add this smaller rectangular prism, which is going to be 4 by 12.5. And this right here is 16, right? So the length you could say is maybe 16. The width is 12.5. And the height, we determined that, is 4. Okay. All right, and then we're going to add, I'm going to go to this next line over here. I'm going to go down here, just continue over here with my 1/2. What's the base? What's the height? And then what's the other height? Well, the base and the height of the triangle, we determined that this is 4. So that's the base and that's the height because those are the two legs and they're perpendicular. So it's going to be 4 and 13.5. And the height is how far back that triangular prism goes, which is equivalent to the width of the pool, which is 16. Wow. All right, look at all that. So we've done it. We've gotten all the numbers we've needed. So now we're going to put this in here and see what we get. All right, so I'm just going to go a little quickly by just doing multiplication. 35 times 16 times 4.5 plus 16 times 12.5 times 4 plus 1/2, which is 0.5 times 4 times 13.5 times 16. I hope I put that in all correctly. And that gives us 3752. 3752. 3,752 cubic feet of volume of water that could fit into that pool. All right, we got B. That was a little complicated. I know what we got there. C, a garden hose is used to fill that pool. Well, that's not efficient. Water comes out of the hose at a rate, a speed, a velocity of 10.5 gallons for every minute. How much time to the nearest hour would it take to fill the pool 6 inches from the top. Oh, Lord. All right. So this means that we want to convert the amount of water first that we're going to put in here um, into gallons, which they gave us. And once we've done that, that's easy enough because once we know how many gallons, we know that it's just a minute for every one of them. But before we do that, they're not filling the pool all the way. We got to subtract some. They're going to do it for 6 inches to the top. So that's a whole other rectangular prism that we need to subtract out of our 3752. We got to subtract out some volume here. So basically, we have the same width and the same length. But what we're going to do is, since the pool is only going to come up to, up here, we need to subtract that height of half a foot, right? That's what it said, 6 inches, which is 0.5 of a foot. So it's going to have a little 0.5 here. All right, that's not that hard. So we're going to basically subtract out a rectangular prism of air on the top. And that part that we're not filling is going to be 35 feet long, 16 feet wide, but a half a foot deep. And so when we get that with our, already have that number, I could just subtract out 35 times 16 times that half a foot. And that gives us our new number, which is 3472. Okay, well, now that I have, that's how much water we're going to have put into this pool in cubic feet. If 1 cubic foot is equal to 7.48 gallons, I'm going to multiply that by 7.48. And there, that number right there, 25,970.56, is how many gallons of water we're putting into the pool. And for each one of those gallons, it's going to take a minute. No, that's not true. For every 10 and a half of those, it's going to take a minute. Well, for every 10 and a half gallons, if it's going to take a minute, I'm going to divide this by 10.5. Right? I'm going to divide it. And I get my minutes right there. Well, it's 2,473.386667 minutes. But they're asking me to the nearest hour. Yeah. Well, we got to know how many minutes there are in an hour, and there's 60. I'm going to divide that by 60. Hit enter. So to the nearest hour, so it's going to be 41 hours. Wow, what a problem. What a problem. Well, just to remind you what I did here in the calculator is here, first we multiplied this by 7.48. We got our answer. Our answer we had to divide by 10.5, which gave us our minutes. And then we divided by 60 to get our hours. Pretty crazy question. All right. I think that I'm going to leave that there. This one we did in class. So if you were in class, you got to see that one. And I think this video is already really long. So I'm going to stop it.